Okay, sorry, yeah, this is so click, please.
Click, please. Okay.
Okay, so before 2002, there are always people, different labs all over the world doing cardiac simulations. They weren't very sophisticated at the time. Strands 2D sheets. So on the left, you see a 2D sheet. In the middle is a block of tissue that's from 1998. That was actually the precursor to Meshalizer. It's called Flounder, showing a crazy type of fibrillation. And then last, believe it or not, on the right, it's a 4-chamber heart model, the Charlie Peskin cable model. And then basically the codes were developed by PhD people. Click. So again, and then what happened is we started imaging, started improving, we started getting, being able to produce unstructured finite element meshes. Ionic model complexity grew, there was more currents. So the days of taking an article and then transcribing all the equations in the appendix into a working piece of code was impossible, not only because of input error, but because of publication errors. And I don't know of any ionic model that was ever published without an error, a typographic error or some sort of equation error. So we needed to move on. So click. So traditionally, how was software developed? Oh, that went ahead. Anyways, basically a researcher's thesis, probably you're clicking too fast. Thank you. So the researcher came in, probably they took their PhD project and they gave it to a PhD, and then you got version 1 of the program, and then click. And then that branched off. A summer student made version 1.1 and click. And then, it got passed down through the labs, click again, and we started getting all these different versions of the code because each had a slightly different feature that they wanted or wanted to do something different. There's a different ionic model, and at those days, they're all hard coded into it, and click again. And then you ended up with a big mess and then you weren't sure which version you were running, and sometimes you mixed and matched pieces, and final click. And you ended up with a piece of software that was pretty rickety, and every student was just concerned about getting their thesis done, and good luck to the person that had to pick up the pieces after them. So this is unsustainable, really, especially if they're researchers. So how do we meet these demands, these challenges? Well, obviously we have to start doing some software engineering. Again, part of the problem is that the cost of developing these tools is a lot. It takes a lot of hours, and they don't really factor that into a grant when you get a grant. They want scientific results. They don't always view building the tools as necessarily a real outcome. And then we also wanted to do a wide range of electrophysiology topics, not limited just atria or ventricles or this particular monodomain propagation, but bidomain, stimulation, as well as recording. And we wanted to use all the know-how we gathered throughout all the years and keep it in the lab. Next, and make it accessible to all. So again, we're constrained because at the same time we're academic, so we have to come up with scientific results, but we have to build these tools to allow us to get our scientific results. And next. So we want to address the challenges within a community as well. So we actually want to expand our software, and we put all this work into it. And then people come to us and they want to use it as well. And for a while, it was just Gernot and I. So in 2002, Gernot came into my lab, and then we decided, well, we realized right away, we started wanting to share code that we have to we might as well make a software program to make a common base, make something that we can build upon. Next. And then later, what happened in CARP? We added unstructured meshing. Before it was just regular grid. So then Tony came along and the meshing software Tarantula. And we had tetrahedra, so we could do unstructured meshes. Then we started working on numerical methods with Rodrigo Weber dos Santos. And Gernot was part of a grant called MOBIS for 10 years to improve numerical methods. So CARP developed that way as well. And then in 2008, we founded a company, CardioSolve, with the first commercial version of CARP that was forked off and used by Natalia Trajanova's lab actually up until this day. They're still running it. It still works. And we did, and then in 2009, we improved scalability to many thousands of cores and did that on the Oxford Rabbit Heart, a really fine resolution mesh, what is 100 micrometer, no, or less resolution.
Down to 1/10 micrometer, the finest one.
Yeah, at a whole organ level, so that's a lot. So, and up until this time, it was Gernot and I managing everything. So it became a bit much. And then especially click. Oh, I'm not being at the slave of the click. No, you went too fast. So at this time we realized that CARP was electrical, but we had the framework in place that we should be able to, and then it was obvious that we had to move, we were going to move into mechanics, and in the far horizon we had fluids. And this was a slide taken from 2008 at a presentation I gave in Oxford, and click. And we're feeling like James Kirk in The Trouble with Tribbles, if you ever remember that episode, is that these are animals, they're born pregnant, basically. So like every good idea spawns more ideas, which spawns more ideas. And then you also get bogged down. If we start making our software available, then we start getting, we start adding features. And then after that, we start having to do bug fixes. And we came overwhelmed. So we realized that we had to go beyond just the two of us to deal with it. And I think at this point, I hand it off to Gernot.
Yeah, so I think in 2010, so with all that unstructured meshing and the improved imaging, so we figured out that numerics has become a bottleneck. So particularly in my lab, we invested a lot in reducing compute costs. We never did anything in adaptivity. I was always worried by the load balancing issue and the complexity. So you may do 10 years of research on adaptive numerical methods and without getting a single paper. So we skipped that. We focused on strong scaling and also smarter modeling. There were a lot of things we did to improve scalability, asynchronous I/O, the property domain decomposition, and so on, multi-GPU, hybrid MPI, and so on. So we really invested into the numerics. But this gave us something that was very tractable on a wide range of platforms. Next slide, please, Gunnar. So with the influx of people with a good numerical background, we started to move towards multiphysics. We did very early on magnetocardiogram stuff, working on photon diffusion with Martin Bishop. Later on, we moved into mechanics, and even later in 2017, we started work on Navier-Stokes, Brinkman, FSI problems, pressure Poisson, and so on. And today, we're also working in modeling, cardiovascular modeling, as boundary conditions for mechanics, 0D, 1D models, and real-time electrophysiology simulations for clinical applications. So here you get a taste of what we're doing currently in the lab. Not all of that is available in openCARP. So this is our internal research simulation engine. Next slide, please, Gunnar. Okay, so one concern of myself with this increasing complexity of simulations is to keep things tractable. I really got worried at some point, and I started to think about a framework that more abstractly describes an experiment. So if you run our simulator, we have about 500 to 1,000 input options. Dealing with that on the command line, good luck. So this was possible in the early days where we had very simple setups. But even this intermediate setup you see in here, a rapid model with a Purkinje system and 2 electrodes for applying a field shock and a pacing electrode in the RV. That gives you a lot of options. That's a fairly complex experiment, but a really complex one with mechanics and cardiovascular hemodynamics. So if you see a command line of that, you are overwhelmed. So I started to work on CARPutils to encapsulate the complexity and also enhance reproducibility. We added regression testing, debugging, and so on. Also to enable sharing, because people kept sending me very complex bash scripts. So to figure out what is going wrong in their simulations. Sometimes it took me a day to get the simulation running on my machine to be able to help. So that annoyed the hell out of me is probably the least I can say about it. It was very hard to reproduce anybody's simulations. And I wanted to have something that lowers the threshold for beginners, makes it easy to run simulations initially, and also to provide training. After you walked the second PhD student through how to initiate propagation, how to induce a re-entry, you are done with it. So you really need some training that people can train themselves and learn how to use the simulator, and you don't want to walk everybody over and over again through similar stories. So that's why we started CARPutils. Gunnar, next slide, please. That's what we're interested in today. This is a combination of CARPutils with mesh tool, a recent thing Oral Lake was generating. So mesh tool is a Swiss Army knife for mesh manipulation, and joined together with CARPutils, we can build really complex workflows where we automate highly complex processes, because that kind of modeling is quite demanding, and to keep control and keep track of all parameters and all these things going on, you have to automate that. Otherwise, you have to train people for years to be able to do this work, and they will be able to do only this thing. So a lot of effort goes into workflow automation. And what you see here, for instance, this is an abstract model of a 4-chamber hard torso model. Everything in a model is abstract, and the simulation engine, and this is actually just a function. So it's an input-output generator. You provide an input to this function, and you get back the outputs, and you use that simulator within an optimization loop. So this is the kind of stuff we are currently working on. I can't advance the slides, please. So in 2018, we had done quite a bit of contracted research. It turned out that actually some of the industries is willing to pay for simulation services, and we figured out that the overhead for writing the software is started to overload the lab, and not everybody was happy in pursuing an academic research career. So we spun off a company, NumeriCor, that would deal with a lot of the development, and also do and offer services to industry. That happened in 2018. We completely rewrote the code from scratch in 2018 to enhance abstraction. So the multiphysics is much harder than single physics, so we need a different level of abstraction. And also we started to build more and more specialized tools. You want to assemble things together to build one custom tool for one thing, and you needed a different kind of abstraction level for that. At the same time, at one of the CARP workshops, Gunnar and Axel approached us. They got funding for this. I never know what it stands for, SOLMES, or whatever the name of that project is. They had funding for building an open source cardiac EP simulator, and they approached us whether we would be interested in doing this together. Gunnar, I know since ages, so, and he's a very good modeler, and I have a lot of trust in him. So we were pondering whether it makes sense or not. At some point, we decided, okay, let's give it a shot. And this is when openCARP, when we started openCARP. So final slide. So people might get confused. So which flavors are around? We are standing today. There's still the CARP legacy code used by Nadal Trianova, but the use of it is and availability are restricted. So to me, this is a dead end. So this is gonna disappear sooner or later. We have openCARP as an electrophysiology simulator. This is an academic research and community project, mostly focused on applied research. So we made the simulator fairly feature complete. There are a couple of things missing, which are our current research, but essentially this is feature complete, but under the condition that's used for academic research. That was our consideration, because we are an unfunded partner of the openCARP project. So the code contribution is a courtesy of NumeriCor. So this is done by, this has been funded on our end by revenues, industrial revenues. So we got for consulting services, we invested into building this code. And therefore, there is this limitation that's used for academic research only. In our lab, we have the CARPentry, the multiphysics simulator, which we are advancing. So there's a lot of numerical work to be done, like FSI and so on. This is attractive for mathematical students or numerical analysts to work on. So this can support an academic career in mathematics. So this is something we are further developing, and this is academic and used within collaborative projects. So it's always for a specific mean within the frame of a collaboration. There's CARPentry Pro, that's an industrial version of our most current simulation tools. This is commercial only and provided by NumeriCor. So there are always options to use openCARP also for non-academic applications, but in this case, you need a different license and have to talk to NumeriCor of the terms and conditions that apply in this case. For academic research, there are essentially no strings attached. We are in the middle of writing a paper on openCARP. The only thing we would expect and hope that people will cite this if they use the simulator for their research. Other than that, you have the freedom to operate in any direction you want. So this is the history in a nutshell. We went over the 10 minutes, I guess, but not by much.